I co-chair this session with Karthik. I never try to pronounce your last name. I don't even dare to. It's out of my league. We are chairing this session. We're going to have 9 presentations. Each presentation will be followed with a breakout room. So we would like the presenter to join the room that we created right after the presentation is over for further discussions about the poster and the presentation. So whoever has any question, they can just join the room and have a chat with the authors. The student volunteer of the session is Samiha Shimi, and she will be driving all the slides. So if the presenter just uses the keyword next, she can just move on to the next slide. So without any further ado, I will pass this to Karthik if he wants to add anything, or if not, we can just move on to the presentation.
It's a great pleasure hosting this session with you, Mona. So my name is Karthik Vaidyanathan. So I'm an assistant professor at the Software Engineering Research Center at IIT Hyderabad, India. So we'll have 9 posters that will be presented online. 1 will be presented only on site. So can you go to the next slide in this? This is just a broad list of the different posters, and we have marked which of those posters will be presented in the on-site as well. So if you are interested and if you are there in Melbourne attending ICSE, feel free to drop by on 20th of May. But anyway, you'll get a chance to interact with the authors, as Mona was mentioning. After all the poster presentation is completed, there will be breakout rooms. So you can have more like a one-to-one interaction with the poster authors. So I think that's it, Mona, from my side. Maybe we can get started so that we don't delay it. Yeah.
So the first presentation will go to Ish Georgievsky. Please pardon if I pronounce your name wrong. Is that right, Ish? How do you?
Ilche.
Ilche.
Yeah.
The presentation is called Software Development Lifecycle for Engineering AI Planning Systems.
Yeah, thanks. Basically, I will move away a little bit from machine learning branch of AI and move towards the AI planning branch of AI, which is another core branch of AI where we try to demonstrate a goal-oriented behavior in various applications. And here on the right-hand side, basically, I have listed several real applications where AI planning has been applied, and these move from logistics through robotics, service composition, space missions, smart buildings, and autonomous driving and video games. Next. So to give a brief introduction of what AI planning is, it's basically summarized in the left-hand side of the slide, where we have a definition that basically AI planning is a knowledge-based AI approach, which is concerned with finding and selecting actions that when we execute them in the initial state of the world, that they will lead us to a state of the world where the user goal is basically achieved. And in the figure, you can see that there is an oval form which represents the planning problem that we are giving as input to the, let's say, AI planning system. And this planning problem can be, for example, manually created by a domain expert, or it can be partially learned from the environment using assuming suitable available data. And then once this planning problem is easily defined, we can input into some plan generation functionality that will generate a plan, assuming that such a plan exists for this planning problem. And this plan then later on can be executed using different functionalities such as execution and monitoring. Execution and monitoring, as in other branches of AI, are necessary because the real world is dynamic, and many expected and unexpected events may happen. So we have to monitor what's going on and whether the plan that we have generated is still valid. So this gives a brief overview with what kind of functionalities we can expect in a typical AI planning systems. And then on the right-hand side, basically, I have introduced some of the challenges that we may face when engineering AI planning systems. And these are basically challenges that we have experienced over the past 10 years of developing systems based on AI planning, and also during the courses that we teach to students at master level. And I have organized them in three categories, basically: complexity, expertise, and a lack of resources. And the complexity says basically that we need to get bogged down with complex tasks, such as devising a suitable planning model that will be the underlying model for our system. Then the knowledge engineering aspects, since it's a knowledge-based AI approach, we have to provide a suitable input to the system, then the overall architecture of the system, and so on. The expertise and savviness category actually says that on one hand, we need in-depth knowledge or extensive knowledge from the domain where we want to apply AI planning. On the other hand, we need an immersed AI planning expertise so that this domain knowledge that we are going to create and the system itself are really suitable to achieve what we intend to achieve. And to put everything together, of course, we need some software engineering skills to perform this. And finally, the last category says that basically we cannot find any tool that can help us provide common understanding of how to approach building such a planning system, and especially such that will operate successfully in the domain, in the application that we want to integrate in. And finally, there is no actually methodology that defines, covers, and treats all the relevant development phases of engineering AI planning systems. And this basically has led us, or me, to the question that this extended abstract deals with: is what development phases should a typical AI planning system go through? How do these phases relate to one another, and how they can be conducted? Next, please. And then the proposal basically is a conceptualization of an idea for a software development life cycle for AI planning systems that consists of 10 phases, where we start with the requirement analysis phases, which in addition to functional and non-functional requirements involves domain-oriented requirements and user-related requirements. The domain-oriented requirements are those basically that are specific to the domain where we want the system to be applied to. User-related requirements are basically sort of a goal-oriented requirements because we want to achieve something with the system, such as a particular optimization or some preferences-based behavior of the system. Next, we move to basically the selection of the planning model, and this is the underlying structure of the system that involves the planning type, the world context, and any other user-related features that we might be interested in. Now, there are many planning types there are many types of planning in the context of AI planning, and this is really important to select the most appropriate one that is suitable for the application domain of our interest. Then we move on to the domain model design, which is basically concerned with creating a domain model in a formal representation that is suitable to be provided as input to the planning model, to the planning system that we're going to develop. And then we move to the architecture design, which is the typical phase for organizing the components that the AI planning system will consist of and how they basically interact among each other. The next two phases are basically the fifth and the sixth phase are for selecting the appropriate implementation. There's a lot of planning technology already available, but this is mostly focused on the plan generation functionality. If we are interested in other functionalities of the AI planning system, that most probably we will end up in implementing this missing component ourselves. And then the next three phases are sort of the standard phases for developing software system, which involve testing, the deployment, and monitoring. with some peculiarities related to the AI planning system that basically I'm not going to go into detail just for the time limitation. And finally, we have the analysis phase, which is kind of important because we have to understand whether the plans that this planning system generate are suitable or are valid for the the initial planning problem that we have set to solve. Okay, so that was the brief overview of this life cycle, and then please move to the next slide, which is the last slide, where I want to kind of give you the three main points that you can take home. And the first one is that this represents an idea of general software development life cycles that can help engineering and planning systems. Of course, it might not be necessary that all planning phases, development phases are needed. Some of them can be excluded depending on the, let's say, planning expertise available or the availability of requirements, for example. Then it's this software development lifecycle also provides the basis for discussion among the practitioners and researchers of both communities, AI planning and AI engineering. And I think this could be especially useful because it moves, it can move the field from being oriented to theoretical approaches to a more practical implementations of AI planning systems. And I really hope that it can be useful to identify some open challenges that are related to some of the specific phases of this software development lifecycle. That was all from my side.
Thank you, Ilce. The next presentation, Tamiya, please. So you will be joining, again, to remind everybody, the breakout room for anybody who has any further questions or want to chat with you about your research work.
Hello.
Hi.
Hello, the next presenter will be presenting about the algorithm debt, the challenges and future paths of algorithm debt. So please go ahead.
Okay. Hello, everyone. My name is Iko Simon. I'm a PhD student at the Australian National University. And this is the result of my preliminary results from my research supervised by Dr. Melina Vidoni and Dr. Fadame Fad. Next slide, please. Okay, as an introduction, technical debt refers to design or implementation constructs that are expedient in the short term, but end up setting up a technical context in the long run that makes maintenance of the software to be complex and challenging. Different technical debt types, such as code debt, architectural debt, and design debt, have been identified in traditional object-oriented systems. And nowadays, the scientific software, which refers to data and algorithm-intensive software, is gaining a lot of popularity. And AI is a subset of the scientific software. And one problem is that the knowledge on these AI systems have not really escalated at the same rate as the popularity. So this has made room for research to be done regarding quality issues in AI systems. And recent research uncovered a type of technical debt that is specific to the AI domain known as algorithm debt, which is briefly defined as the suboptimal implementation of algorithm logic. However, this definition has an issue which I will point out further. Next slide, please. So basically, the aim of this research is to motivate reflective discussion on algorithm depth in AI software by summarizing the challenges, the impact of algorithm depth, and also outlining future areas of work. And for us to understand the impact of this work, I will give real-world examples of cases in which issues with algorithms had a tangible repercussions on the companies implementing them and also on people's lives. The first one is in 2012, the development team of a financial company was pressured to complete changes to their algorithm, which led them to take considerable shortcuts to speed up the process, which made the company to mistakenly buy stocks worth $7 billion with an additional $440 million in loss. And yeah, it wasn't really clear as at that time what the issue was, but it was later discovered that the fault was from the implementation of the algorithm. As a second example, in 2018, Arizona recorded a pedestrian fatality where a person was struck by an Uber test vehicle while crossing the road. The alleged cause was that the algorithm failed to classify the human pedestrian as a human. Yeah, there was actually a fault with the algorithm. And another impact of algorithm depth is that due to AI being a package-based software, if a framework that is being used in the development of an AI system is flawed or is having algorithm depth, every application that uses that framework will transitively suffer from algorithm depth. Next slide, please. So this research, from this research, I was able to identify some challenges. And the first challenge is that there is no standard accepted definition of algorithm depth. The question is, if there is no definition of algorithm depth, how do we study it? It becomes impossible to study what cannot be defined. So the current definition, as I said earlier, has a flaw. The flaw is that it was not derived from a systematic study, but rather it was derived and it emerged from the definition of the current code depth. Another challenge is that the algorithm depth tends to increase code complexity. Previous research has shown that technical depth tends to decrease the readability of a code, that is from a developer's perspective now, which tends to increase the complexity of the code, making future maintenance to be difficult. And then the other challenge that has been we identified is that there is no definition of what algorithm depth smells are. So automatically identifying algorithm depth will be challenging, given that there is little knowledge on on what the causes are and what the smells and how the smells present themselves. So the next thing is the future directions. Next, please. Okay. In order to solve this issue of algorithm depth in AI, the first thing is to get a formal definition of algorithm depth from a systematic study, as this will allow us to investigate how algorithm depth varies across AI and other scientific disciplines. The next future work is to identify unique smells of algorithm depth, because without understanding algorithm depth's unique smells, it will not be feasible to thoroughly analyze what its causes are and then its repercussions on the performance and behavior of AI-driven software in order to be able to mitigate it in the future. Then the last future direction is to investigate the impact of algorithm depth in AI software. Given AI's current pervasiveness and the continued ethical discussions, it has become necessary to understand what are the impacts that algorithm depth has on AI systems, because by doing this investigation, it gives us an idea of how to also mitigate on the steps to take to mitigate algorithm depth in AI systems. And then finally, we live in a world whereby AI has taken charge of basically everything from our research work to the appliances we use at home. This gives importance to the algorithms that are being used to implement these AI systems. So by the time these AI systems are faulty, it would definitely translate to the applications that were created using these algorithms. Thank you.
Thank you, Emmanuel. So we can go for the next one, which is Enabling Machine Learning in Software Architecture Frameworks by Armin Moin et al. I hope someone is there for this. Anyone? Because I couldn't find in the participant list. Okay, so maybe I think Samiha, we can go to the next one, which is Extensible Modeling Framework for Reliable Machine Learning System Analysis by Jati Hilamshia Hussain. I hope I didn't kill the pronunciation of the name.
That's right.
Yeah, thank you. So please keep a sec on the time of 6 minutes. Thank you. Go ahead.
Okay, so yeah. Okay, nice to meet you all. My name is Jati. So I'm from Waseda University. So basically this is our early step for the next phase of our research. So this is a research project that have been conducted by corporation of Waseda University, Telkom University, Musashi University, and Fujitsu Limited. So yeah, I'm the representative for this case. So again, the title is Extensible Modeling Framework for Reliable Machine Learning System Analysis. So next, please. So yeah, again, like what I said, so we have a previous work on this side of things. So we already have a framework which called Multi-View Modeling Framework for Machine Learning System. Usually we abbreviate it as MQS. So the idea is we want to have a three-peak approach to analyze and synchronize ML system design and the ML training pipeline. So like usually we want to measure the performance of these labels and that's kind of stuff, but sometimes we don't really know what's the specific limit, like what, let's say we want to have a precision for pedestrian, but what is the specific value that really we need for achieving a reliable system? So that's the basic idea of our modeling framework. So we have a system models, and then we have a configuration that connects into the ML pipeline. And from the abstract side, during the iteration, we will go into the tail side of thing. And all of this is supported by integrated meta model. So that's our previous work. But in our journey, we found that it still has challenges. So again, when we talk about models, different project has different domains, have different problems. So different set of models may be needed. So that's one thing. And the second one is maybe at first we don't really care, let's say, about safety, but in the later phase, we got more into it because let's say, yeah, let's find working things first and then we can add it later. So a new concerns may arise later at more detailed phase. And for modeling, this is a common problem. When we talk about organization, usually they have their own set of models, And even when we have a specific concern, same concern, let's say we want to model the functionality, each organization may have their own model to specify that. So we want to solve that. And to extend our approach into more general side of implementation, so we try to look into the ISO IEC IEEE 14764, and this is basically the standard for software lifecycle process in the maintenance. And we made the process to extend and modify existing process of MQBase. So we have the basic side of things, which is the model itself, and then the meta model. But we try to make it, not really try, but we push the ML concern into this side of things. So we start by the definition of the need for analysis. So let's say we want to think about the safety, the functionality, the ML pipeline, or other stuff. It needs to be specified in the definition for the need for analysis, and it is based on the ML training concern. And then we go into the responsibility mapping, which I will show on the next slide. And this mapping basically has a established process and see whether it's fit there and what's missing and what's too much. And then if we found something is missing and something is excess, then we can propose modification, and then we evaluate it. Is it suitable or not based on the cost, based on risk, and then we can review and accept or reject the change. In case of the acceptance, the meta model will need to be updated, and then we will add the monitoring concern, because our framework has the concept of ML monitoring concern into the system modeling itself. And then we run the pipeline again, and we monitor the potential drift. And then if it found, and we have found a significant drift, the process may change again. The evolution process may happen again, because maybe, just maybe, we choose a different kind of model that has gap, so we don't really analyze that part. So that's the basic idea of the evolution drifting. Okay, so maybe next.
One more minute, Jati.
Okay. Well, okay, so yeah, basically this is just demonstration. So we can see on the left side how the responsibility mapping works. So if you want to see more, just come to the breakout room. And like we have a previous process which more about safety, and we put it into the table and see which part is missing, because we want to have more behavior-oriented modeling process using activity diagram. And yeah, that's the basic idea, and we base it on standards or machine learning workflow from Microsoft, and then we update the meta model, like addition or removal of elements. So I don't know how many seconds that is, so let's go to the next slide. Okay, next please. Okay, so basically we the previous slide actually based on the case study, and based on that limited case, we found that it can be extensible. So that's what we found right now. But sadly, it's really limited. So we want to find out more the generality. So we will use more different cases, maybe using Archimate or another type of model that we want to try, and different domains. And one thing that really excites us is how to update meta model in more systematic manner. That's what we will try to figure out. So yeah, I guess I hope I don't break the limit. So yeah, I'll return it to you.
Great, thank you, Jati. So thanks for the presentation. So next up we have the next poster on how federated machine learning helps increase the mutual benefit of data sharing ecosystems by Eva Krasteva. So I think Eva, you're there.
Yes. Hello.
Yeah, great. Go ahead. Yes. Yeah, you're audible.
So, yeah. Hello, everyone. So my name is Eva, and I will briefly present a work in progress paper co-authored with my colleagues, Boris and NCA. Basically, the proposed approach is based on federated machine learning and data spaces to increase the mutual benefits of data sharing ecosystem. So next, please. Data spaces are an emergent paradigm which is based on federated software infrastructure and supports sovereign and secure data exchange between the participants in the data space. One important characteristic of data spaces is that the data is stored within the internal systems of the data provider and is only made available when the data is needed and under certain conditions, which are called usage policies. But furthermore, actually, data spaces are communities in which value for the participants is created through the use and reuse of data in various data sharing scenarios. However, providing access to the data might not always be possible for the data providers when they're dealing with different kinds of sensitive data. Actually, our approach addresses this particular issue for sharing sensitive data. So next slide, please. For the implementation of the approach, we use the data spaces reference architecture model defined by the International Data Spaces Association, which actually specifies basic components, roles, and exchange protocols. For the sake of this presentation, I will only outline two of the components. The data space connector and the application store. The data space connectors within a data space act as gateways between the internal systems of participants and the other components of the data space. And they are responsible to handle all the communication between the participants and to realize the exchange of the data. The App Store component on the other side is a dedicated component for trusted applications which can be downloaded and executed within the data space connector. So our approach uses these two components in particular. And next slide, please. Yes, as I said, our approach uses these two components to realize an optimization of traffic prediction algorithm, which uses data by different traffic network companies, which are not willing to share their data explicitly. That's why actually the federated machine learning algorithms are executed within the private environments of the data providers, where the sensitive data is stored, and only the output of these algorithms are shared afterwards. Next, please. Actually, yeah, as a future work, we are working on a use case with 3 competing transportation network companies who are participating participating in a pilot urban data space. And we want to use this for validation of the approach. In addition, this approach can be applied in and replicated in different application scenarios. So we are also looking towards this. Yeah, and next slide. Yeah, so thank you. And I and my colleague Kensia will be expecting you in the breakout room.
Great. Thank you so much, Eva. Yes. So we have the next presentation, next poster, which will be on maintaining and monitoring AI ops models against concept drift by Lorena Poenaro-Laro. I hope that pronunciation was right. So Lorena, if you are here, you can get started.
I'm here.
Great.
Hello.
Great.
So how will we do? Like, how can I change the slides? Should I share my own screen?
You just need to say next because the slides are already being shared. So you just have to say
Okay.
next and we'll be in the next
Yeah.
slide. Yeah.
By the way, just to mention, I uploaded a new version because it was not on the good format. So
Oops. Okay.
I just uploaded it, so sorry.
I think Samiha, you can play it directly from there.
Oh, okay, then I can share my screen. Oh, I
No,
cannot.
I'm saying the volunteer will directly play it from there, I guess.
Okay.
I don't see it here.
It should be called maintaining and monitoring. So I uploaded it a few minutes ago.
Maybe shall we go to the next and come back to this? Is that okay? For the sake of time.
I can also present on the old slide, so it's okay.
Okay, fine. Then can you quickly do it then?
Should I stop sharing?
Yeah, once she shares, probably, yeah, you can.
So shall I try to start sharing my screen?
Yeah.
Okay. Yep. I think you can see my screen. Great.
Yes, you can put on a slideshow and you have 6 minutes. You can start. Thanks.
Yes. 1 second, because I cannot hide the bar. Oh, sorry. But I cannot press this. Ah, now I can.
It's on the bottom also as well. Yeah, great, great. Yeah.
Okay. So hello everyone and welcome to my presentation. My name is Lorena Poenaro-Laro, and today I'm going to talk about my current work, which is regarding maintaining and monitoring AI ops models against concept drift. So basically, what is the main problem? Well, the main problem is concept drift. And what concept drift is actually changes in the data over time, which is actually happening a lot in AI ops models. And it's a significant threat to their performance over time. And this concept drift was also observed in previous work in disk and job failure prediction. And why is actually this a problem? Well, let's look at the evolution of AI ops model over time to understand a bit better. Let's see how we create a model. We have data until a particular point in time, which is our training data. We use this data to train an AI ops model. And then we expect this AI ops model to be able to give us predictions for our testing data. And the problem is that the machine learning algorithm that is used in this AI ops model assumes that the data distribution does not change over time, which is actually a false assumption in terms of AI ops model, which is constantly changing. So this results in performance degradation. So basically, AI ops model needs to be monitored against concept drift and to be continuously maintained. Now, I created this pipe. I extracted this pipeline from this source over here. So this is the pipeline of AI ops models in production. And then I'm going to discuss first about our vision regarding model monitoring. Our vision is we want to answer the question how to monitor these models against concept drift. And the answer is actually concept drift detectors. The concept drift detectors can be included in this step over here. So every time in the evaluation, test the evaluation data to understand whether concept drift occurred. If the drift was not detected, then you can just continue with the model as it is in production. But what kind of drift detector can we actually use? Well, actually, there are plenty in literature, and yeah, we don't really know. The idea is that AIOps models are really label expensive. So these concept drift detectors can be label dependent or non-label dependent. So the best concept drift detectors to use in case of AIOps models are the concept drift detectors that do not require the labels to detect concept drift. Now, our next questions would be how to choose a concept drift detector or what to do after we detect concept drift. So what to do when we detect concept drift? Well, we can go to the next phase, which is the drift identification. And this drift identification is basically understanding the severity of the drift. So how dissimilar is our testing data compared to the training data? How much would be our model's performance affected? And yeah, this is basically trying to understand how different the data is. So after we identify the severity of the drift, we will apply the appropriate model maintenance technique. So basically we need to retrain and update the model. And this maintenance step, we're going to do according to our previous steps. So basically we might expect that, for instance, for a strong severity of the drift, we might need to do another model with the current data. So we should definitely forget the data that we were using before because it's totally different. Or for a lower severity, we don't need to do that. So now the question would be like, which retraining technique to use and on which data should we retrain? And this all depends on the drift severity. Now, let's discuss a bit about the future work. Firstly, we will go about model monitoring. What it is here to explore. Firstly, how can we actually evaluate these concept drift detectors? So how can we know that they are able to detect when this concept drift occurs? And the second question would be how to understand which concept drift detector to use during the model development phase. Now, from the model maintenance perspective, we have the drift identification step in which we need to understand how to properly identify the severity of the drift. So what are the characteristics of the data that can tell us the severity? From the model retraining perspective, we need to understand what type of retraining does each drift severity require. So for instance, in the case of a severe drift, should we just simply discard all the data, training data that we have, and should we only train on the new, or what other technique can we do? So shall we actually train only on the new data or on all the available data? And the other question would be how to maintain these AIOps models when obtaining these true labels is extremely expensive. We need to retrain our model, but what if we cannot obtain the true labels until the end of the year, given that we are at the beginning of the year? What kind of solutions can we find here? So can we actually retrain on some noisy pseudo labels instead, which are kind of some fake labels combined with the true labels to help in performance preservation? Or would this noise actually affect the model performance even more? With this, I would like to thank you for your attention, and here you can have all my contact details if you want to discuss more about this subject.
Great. Thank you, Lorena, for a nice presentation. Next up, we have the next poster, which is reproducibility requires consolidated artifacts. So I'm maybe Samiha. We can share it. Great. So just a reminder for everyone here, we make sure that you are there till the end of the session. We'll be having breakout rooms. You'll be able to interact with the poster authors. So that will be a great opportunity. So yeah, Dennis, I think, yeah, you can go.
Okay. Hi, everyone. My name is Bowman Brown. Oh, sorry about that. My name is Bowman Brown, and I'll be presenting reproducibility requires consolidated artifacts. I can probably jump right in. So next slide, please. So effectively, machine learning is facing a reproducibility crisis. As some of you may have encountered in your own work, a number of previously published studies have results that cannot be reproduced, either by the same authors or using the same code or by other authors. And effectively, this is a huge issue with research in general, and is something that needs to be resolved. So what we did was we performed an analysis of the Rescience C journal, which is a reproducibility study journal. Effectively, they take previously published works and they try and reproduce them. And the reproductions are reported alongside the issues that they faced, whether or not they could actually reproduce the results, and then other factors that may have influenced the final process. So we analyzed these studies effectively to find what factors contributed to a failure of reproducibility. And what we found from the 142 papers that we analyzed were that roughly 20% were unable or partially able to reproduce results, in the sense that they were able to reproduce a subset of what was published. But that the factors that most contributed to the failure to reproduce were a lack of hyperparameters and a lack of code. So with that in mind, I think we can probably jump to the experiment section. Next slide, please. So we wanted to evaluate how these lack of artifacts, specifically with configuration and hyperparameter details, influence the results. So we set up an experiment where we looked at the NATS bench dataset. A NATS bench is a neural architecture search dataset that contains a number of different architectures, both ResNets with residual connections and then architectures without residual connections. And we wanted to apply different search strategies to these architectures and effectively evaluate against the benchmark baseline. So the benchmark, of course, has average performance over all of these different architectures, and we can compare how our search strategies bias the results. So I think if we jump to the next slide, please, I can talk a bit about the results. Effectively, we found there was significant bias. So you can see here that the more random strategies, greedy and Sobel sequence, tended to perform on average closer to the true performance of the data set, whereas some methods such as tree parse and estimation were over, and other methods that sampled from variance and more Bayesian optimization approaches actually underperformed. So what this tells us is that these missing configurations can have a significant impact. If you're looking to compare results that are produced under different hyperparameter configuration strategies, you might entirely bias your results by comparing, for example, your method with TPE against a baseline method with random search. So I think mainly our results showed that there's a requirement for reproducible results and reproducible analysis, that all configuration artifacts and all artifacts in general be presented with a publication. So we want to make sure that hyperparameters aren't split out in the paper, in the code, as well as they could be using default baselines from underlying libraries. All of these factors contribute to a lack of detail and a lack of information, and then result in these issues with reproducibility, and then of course can completely bias the results for the final output. I think we can jump to the next slide. So as I mentioned before, failing to account for hyperparameters can significantly bias your results, can lead to incorrect analysis, and effectively is a significant contributor to the reproducibility crisis in machine learning. It's something that needs to be solved, and effectively new tooling is one of the major, I would say, directions that can be improved in order to facilitate sharing of artifacts, sharing of code, and ensuring that the complete configuration is shared along with any results. I think in the interest of time, that's probably it for me.
Thank you. Thank you, Bowman, for this nice presentation. So next step, we have Tenet, a flexible framework for machine learning-based vulnerability detection by
That's me.
Edward.
Yes.
Yes.
Can I share my screen because I have some animations and I want to be synchronized with the animations while I'm presenting. Is that okay?
Okay, go ahead. Yeah.
Thanks. So can you see my screen?
Yes, you can start. Thank you.
Okay. So hi, everyone. I'm Edward Pinkonski, a PhD student at FEO, and I'm specializing in software security engineering. And today I'll present to you my collaborative work with Carnegie Mellon University and Instituto Superior Técnico on the project titled Tenet, a flexible framework for machine learning-based vulnerability detection. And the aim of this project is to develop practical pipelines for software vulnerability detection, which I'll refer to as SVD. So I would like to acknowledge the support of Carnegie Mellon Portugal program and Fundação para a Ciência e Tecnologia for sponsoring this research. So our goal is to introduce a modular framework that enables the creation of end-to-end customizable, reusable, and automated pipelines for SVD. And by end-to-end, we mean a comprehensive process that encompasses the collection of real-world data through the evaluation of state-of-the-art machine learning models. And we refer to customization and reusability. We highlight here the importance of configurable processing units that can be employed in various contexts to form a cohesive whole. And lastly, we have automation, which plays a crucial role in streamlining the entire process. So our team initially aimed at developing a fine-grained approach for SVD in JavaScript. However, our initial implementation resulted in a complex structure of Python and Bash scripts, and that limited our ability in expanding the workflow, replicating results, and conducting new experiments. And to address these issues, we realized the significance of effective and robust pipelines that allow for a principled approach to ML-based SVD. And our framework aims to overcome these challenges and contribute to the existing literature by addressing automatic construction of datasets and streamlining the entire SVD process. So now let me provide you with a brief overview of our framework named Tenet. And we have built it on top of SEM and CLI framework in Python. And Tenet offers 6 handlers, allowing for multitasking, file and code parsing, and interaction with GitHub and Docker APIs. Tenet follows a plug-and-play architecture, providing a generic handler that guarantees access to the other handlers. And this facilitates the implementation of plugins with specific functionalities. And to achieve our fine-grained approach, we have developed a total of 16 plugins covering tasks from ranging from data collection to modeling. Tenet is publicly available and can be accessed at the following link. And I will next demonstrate how we implemented our fine-grained approach by using these plugins. So our approach consists of several components that leverage the aforementioned plugins, and I will shortly go through each component. So we have a data collector that gathers metadata from sources like National Vulnerability Dataset and open source vulnerability dataset. And we retrieve vulnerable and fixed source code using the GitHub API. Then we have a data labeler, which provides 2 strategies, diff analysis and static analysis. And the formal labels code by analyzing changes between vulnerable and fixed versions. And the later uses static warnings generated by static analyzers. We have a granularity adjuster that identifies the boundaries of functions that the code changes have using JS code shift. We have a representation extraction where we use AST miner to extract functions or context paths from the source code. And then we have a data pre-process and sampler, which balances, stratifies, and splits the data into multiple sets. Then we supply these sets to the model training, which accommodates several models ranging from basic machine learning to state-of-the-art ones like Code2Vec and CodeBird. And additionally, it can be easily integrated with other models. And lastly, we have a statistics component that generates multiple plots to visualize the data and collects metrics to evaluate the performance of the models. These components can be organized into different pipelines, and we currently provide two end-to-end pipelines to produce state-of-the-art models for JavaScript with Code2Vec and CodeBird. I have here prepared a demonstration to show our approach in practice, but I think I don't have time to go through it, so I'll leave it for the breakout room, and I'll skip it. In conclusion, Tenant is a versatile framework for building ML-based pipelines for SVD, and it has a modular and customizable design that addresses the challenges of complex configurations and manual installations to enable automation and reproducibility. And we plan to enhance it with user-friendly web interface and provide labeling with human feedback. Thank you for your attention, and that's it.
Thank you, Edward, for this wonderful presentation. So last but not the least, before we go to the breakout rooms, we have the poster towards understanding machine learning testing in practice by Arumoy Shome, if I'm not wrong with the pronunciation. So Arumoy, are you there?
Yes, you got it almost
Yes.
right. It's Shome.
Oh, okay, Shome. I'm sorry. Yeah.
Yes,
Great.
no worries.
So go ahead.
Yeah, thank you for the introduction. Thank you all for staying right till the end. I know it's been a very long day for some of us, especially if you're joining from Melbourne. So I really appreciate that. Quick round of introduction. I'm Arumoy, or Aru. I am a PhD candidate at the Software Engineering Research Group in TU Delft from the Netherlands. I have the privilege of working with excellent researchers like June, who is also joining here, Luis and Ari. I'm in my second year, and I'm happy to say that I've seen the light. So I've found my calling, and so in this presentation, I hope to present, or I'm going to present what I envision to be working on for the remainder of my PhD. Two quick disclaimers before we move forward. I did change the title of the presentation, and that's because when I submitted the poster, we still didn't have a clear idea of where we were going, but I think in the months that followed, the idea is really matured. So I really thought that the new title fit better. Final disclaimer is that some of the stuff that I'm going to present is unpublished work. And presenting unpublished work is always a risk, but Luis has convinced me that this is a risk worth taking. So I'm really hoping that you're as excited about this topic as me, and I'm really hoping for some nice discussions and some feedback. So let's go to the next slide, please. So machine learning testing is important, right? So I'm not going to list out why that's the case. We are software engineers and we are attending CAIN, so I can assume that we all appreciate that fact. There was also an excellent paper that came out a few years ago from King's College London. I think she's attending CAIN. So that paper really presents a nice overview of the research field that is machine learning testing. But I think one thing that's been missing or has been neglected till now is the fact or the role that that visualizations play in machine learning testing, right? So, and I think especially it's very interesting to see visualizations that come earlier in the more data-centric phases of the machine learning lifecycle. So these visualizations really follow or go for a more exploratory style. So typically they tend to be very quick, very dirty, and they're used to make sense of the data. but they're there for a reason. And I think in a way, I think the domain expertise and the knowledge of the practitioner who's creating the visualization is embedded in that visualization, right? And we tend to make decisions or assumptions of things later. So we make assumptions for the models we select or the data transformations that we do based on these visualizations. So this works really well when you're working on your laptop on a Kaggle competition or a assignment. But when we want to go to a productionized system, these data properties that we're looking for, they tend to become more latent. And the problem now is that machine learning systems never fail explicitly, right? So if let's assume our data changes, our machine learning model is still going to continue to perform, albeit with a worse performance. So I think that there's this research gap between going from these implicit expectations that we have in our visualizations for data to a more formal way of specifying them, so that we can we can go to a more productionized system. And there are many benefits for doing this. One, now we have tests that fail explicitly and they can be verified across the machine learning lifecycle. It scales across organization or team changes, and it also scales across large-scale production systems when you're dealing with big data. So I have an example here. So typically the test for normality on the visualization side, we look at histograms or we look at QQ plots. And an analytical test would be to do the Shapiro-Wilk test. Next slide, please. So the good news is that we have a rich source of finding these visualizations. So that's Jupyter Notebooks. The bad news is that they're really difficult to find. So that's what I've been focusing on for the past month now. So the way we are attacking this is in a two-prong approach. The first part was to do a small-scale manual qualitative analysis. And for that, we adopted two search strategies. One was to look at Kaggle. And we were looking at the top submissions of the top competitions with the highest reward. So the motivation behind that was that we can motivate that this is really serious people. So they are practitioners who are working in the field of data science and machine learning. And we can expect that we don't see toy projects, right? So, and then the other search strategy is to look on GitHub, and we are doing some simple static analysis to create a search pattern and find visualization. So in the week before I got on the flight to Melbourne, I found 3 properties. So I think 3 data properties or interesting visualizations. So I think we are on the right path. And the next step now is to obviously scale it to a much larger data set. So we are also lucky there because we have 2 very nice data sets from MSR. One that has, I think, notebooks from GitHub, and that's in the scale of a few gigabytes. And the other one is notebooks from Kaggle, and that one's in the scale of some terabytes. So that obviously requires a bit more engineering work, but that's the immediate goal would be to move towards scaling up to a larger set. Next slide, please. Okay, so in terms of short-term goals, I think our objective now, or what we're hoping to achieve, is formally define this new form of testing, which we've been calling visual tests, and recommend. So find a handful of these examples and recommend analytical tests that practitioners can use. But the ultimate vision that we have is to obviously have an automated way of doing this. So a tool, for instance. So we really want to recommend these analytical tests to practitioners in some form of plugin or a tool. And I think that if we succeed in reaching that stage, then we have a very nice source of data, because Jupyter Notebooks give us 3 very unique perspectives. So we have text from the practitioner, we have the code that generates the visualization, and we have the images, right? And that's my focus for the PhD, but I also think that there are many nice opportunities for collaboration here. So I think things like reproducibility and code quality in notebooks things like explainability and HCI, I clearly see a link here, and I think there's room for a lot of interesting collaborations. Yeah, that being said, thank you for your attention. I think I was a bit too quick, but I hope the idea was interesting enough to generate some nice discussions, or it was interesting enough to trigger you. Unfortunately, I won't be available to stay for the breakout, but I'm here in Melbourne. Please connect with me. Please feel free to approach me, and let's have a discussion. Thank you so much.
Great. Thank you, Almoy, for this excellent presentation. I think we are done with the poster presentations. So thank you all. So what we are going to do now is we are going to create breakout rooms where each room will have the name of the posters, and you can just join the corresponding rooms so that you can talk to the authors, interact with them. I think all these posters have been excellent. So I'm sure that you will have some great discussions with the authors, and of course, feel free to interact with the colleagues who are entering the room as well. So Samiha, let us know once the rooms are ready, and we'll be ready to go.
Yeah, I'm working on this. Just give me a few minutes.
Cool. Yeah.
And just to add to what Karthik mentioned, you don't have to just join one room, right? You can just like move around.
Yes. I think we still have like almost 40 minutes till the next keynote, so we can use that time to go around and interact with different poster authors.
So Samia, you just need to create 8 rooms, right? The last presenter is not going to be here, and
Okay.
then the AI, the first one did not attend, so it's just.
So the enabling machine learning, that was not presented, right? I don't see any participants.
No, that also is not
Okay,
there. So
okay.
you don't have to add participants. I think for now we can just create the rooms and leave it there.
Oh, okay. Okay, I have 1, 2, 3, 4. I have created the rooms, 7 rooms.
Great, but we don't see that. Maybe you can leave the participants to automatically select the rooms. There is an option, I guess.
Okay. Actually, I have assigned only 2. Other ones are like I haven't assigned. And room in progress. So can't you see them?
Not me though.
Dr. Raimi, can you see the rooms? Like they are in progress.
I'm assigned to a breakout room, but it's the wrong one.
Okay, sorry about that.
So maybe I think it should be the second one in the list.
Oh, AI planning.
Yeah.
I think I named it wrong. Let me rename that.
Oh, okay.
Okay, I'm just recreating the room. I cannot see that option. So I have renamed your room. Can you see the rooms now?
Yes, now we can see the breakout. So there is a breakout room option enabled below in Zoom. So you'll be able to select the room from there and join in.
Very good. And we can go back and forth between the rooms as we want, right? We can go back to the room, then very good. Excellent.
Thank you, Samiha.
So let's do that. Great. Thank you, Samiha.
No problem. Thank you. Sorry for the confusion.
No worries. Yeah.
Should I just stop the recording now?
I think so. You can, because the session kind of is done. It's more interaction. So.
Okay.